So, on the name of casting, what are the what are the disadvantages we had seen? Can anyone tell me the disadvantages? See, one was machining is required, right? Because we are not getting very good surface finish. And the other one was dimensional accuracy is less. So these are the two main disadvantages. The dimensional accuracy or the dimensional tolerance we say. The dimensional tolerance is not good. That is one thing. And the surface finish we get is not good. So these both disadvantages are the disadvantage for sand casting. These both are the disadvantages for sand casting. So to remove these disadvantages, some other casting methods have been developed. These casting methods are shell molding, investment casting. So let's have a look at all these casting processes. First one is shell molding. So you can see on the secondary screen, I have made a diagram. I have kept a diagram there. Okay. So I'll explain what is happening here. This shell molding. So here we take a hot pattern. This is a heated pattern. The top portion that you can see is a pattern. This kept over a box. Inside the box, we have sand along with phenolic resin. In the labeling, it is mentioned only as sand, but it is sand plus phenolic resin. The phenolic resin is acting as a binder. Okay. Now the total setup is inverted. In the second diagram, you can see the total setup is inverted. When we invert the setup, because the pattern is hot, the resin, the phenolic resin and the sand will form a layer over the pattern. Okay, they will form a layer over the pattern, and then again we'll invert the setup. So you can see the step 3. In the step 3, again the setup has been inverted. So when the setup is inverted again, whatever the remaining loose sand was there, it simply falls back. Then whatever the layer was formed, that layer is removed. And similarly one more layer is created. Both these layers are kept inside a box. A flask. Thus a mold is made. Okay. Here, so the mold is made in the form of shell. We created two shells, right? And the mold is in the form of shell. That is why it is called as shell molding. You can see here, it is a molding. The name is molding. So in this process, we are making the mold. Okay, Now what happens is, the shell that we have created is having very good surface finish. Because of this good surface finish, the final casting that we get is having very good surface finish. Okay. How to separate the pattern and shell? Danish is asking how to separate the pattern and shell. See, there are ejector pins. In the step 4 diagram, you can see there are ejector pins. When you push the ejector pins, the shell will be lifted. Okay. So that is how you separate the shell and the pattern. Then Vishes is asking, so very complicated parts cannot be made. Yeah, like mostly very complicated parts cannot be made by this. How shell becomes hard? Yeah. The entire thing will be again kept inside an oven. So that the phenolic resin melts properly and it solidifies properly. Okay, that's how we make the shell hard. Okay. Injection molding is just like the injection, and that there is whatever you want to make, it is in front of a plunger, you will push it. What the material will go into the cavity. Okay, that is injection molding. I'll show you how an ejector pin works. Okay. The shell molding is a casting process in which the mold is a thin shell of 9 mm thickness. It is not necessary that it will be always 9 mm. Okay. So it is just a number for your imagination. Shell of thickness 9 mm can be made. This is made of sand held together by thermosetting resin binder. Thermosetting resin binder means we are talking about the phenolic resin. Okay, a metal pattern is heated and placed over a box containing the sand mixed with the thermosetting resin. The dumb box is inverted so that the sand and resin mixture fall on the hot pattern, causing a layer of the mixture to partially cure on the pattern surface to form a hard shell. The box is positioned to previous stage so that loose and uncured sand particles drop away. Sand shell is then heated in oven for several minutes to complete the curing. Okay, so this is the answer for Danish question. Danish asked, sir, how does a shell become hard? Danish, so you can see here, the sand shell is heated in an oven for several minutes to complete the curing. The shell mold is removed. The shell mold is removed from the pattern and two halves of the shell mold are assembled, supported by sand or metal shot in a box, and pouring is completed. Now Danish is asking, what is the pattern material? Because it should have good adhesive. It should have good adhesive. Danish, again, if the adhesive property is good, it will be difficult to separate the pattern. It will be difficult to separate the pattern. So good adhesive property is not necessary. Only for the initial stage good adhesive is necessary. That too is achieved because of the heated phenolic resin. The heated phenolic resin itself is quite like an adhesive in nature. It is like a binder. So it will bind over the pattern. And to the part about what kind of pattern material is used, Danish, in shell molding, metallic patterns are used. In shell molding, metallic patterns are used. Very popular question asked in different small exams. What kind of pattern material is used in shell molding? Metallic patterns are used. Okay. You can see in the next slide, the surface of shell mold is smoother than conventional green sand mold. The surface of shell mold is smoother than conventional green sand mold. This permits easier flow of molten metal during pouring and better surface finish on the final casting. Okay, start with the diagram. First start with the diagram. Then this slide. Sir, any reason which we can extract? We are studying on phone. Okay. For metallic pattern, like Danish, are you asking what is the reason for taking metallic pattern? One of the reasons that I understand for taking metallic pattern is, see, first of all, we need a very hard surface so that a proper layer can be formed. So by using mercury and wax, it will be slightly difficult for this process. Next comes the surface finish. On the metallic patterns, you can get very good surface finish. So if the surface finish on the pattern is good, you'll get good surface finish. You'll get good surface finish on the shell also. That's why we go for metallic patterns. And on the metallic patterns, you'll get good surface finish and you'll get good surface finish on the shell. So overall, you'll get a good surface finish. Okay. Okay. The surface of the shell mold is smoother than conventional green sand mold. This permits easier flow of molten metal during pouring and better surface finish on the final casting. Surface finish of the order 2.5 microns can be obtained. Good dimensional tolerance of plus or minus 0.25 mm can be reached in a small to medium sized parts. Okay. Machining operations are reduced because of good surface finish. Already we are getting very good surface finish, hence we don't have to do much machining. It can be mechanized for mass production and will be economical for too. And it will be economical too. See, what happens is, the metallic patterns that we make, these are quite expensive in nature. Okay, these are quite expensive in nature. So, if we are making that metallic pattern for casting only one component, then it will become very, very expensive. So, shell molding is justified if you are producing large number of components. If you are producing large number of components, then it is justified. Okay, just for one casting, making a metallic pattern is quite expensive process. Okay. Expensive metal pattern is required, hence not suitable for small quantities. Application for making cylinders, cylinder head of IC engines, gear blanks. What is a gear blank? You can take, what is a gear blank? Gate blank is the initial plate on which you cut the gears. Gate blank is the initial plate on which you cut the gears. Okay. So whoever wants to take the pic, I'm keeping the first image, start taking. I won't repeat this. Let's move to the next process. Next one is slush casting. Next one is slush casting. Okay. So slush casting is somewhat similar to the shell molding. How? Let's see. Let's suppose you want to make a bowl. So what you will do is, you take a cavity of this shape. Inside this cavity you will fill the molten metal. Okay, you have taken a mold of this shape. This mold you have filled with the molten metal. Now you will invert the entire setup. So what you will get is, as of now you won't invert. You will wait for some time. So when you wait for some time, solidification will start taking place from the wall. Right? Some portion will get solidified. The solidification has started from the mold wall. By using shell molding, only symmetrical parts can be made. You can see from the examples itself. Now we'll invert the setup. When we invert the setup, whatever excess molten metal is there, it will simply flow. The excess molten metal will fall down. Okay. Then we'll remove this solidified portion. And here we get the casting that we wanted to make. Whatever casting we wanted to make, here we have got that. Okay. So this is the shell molding process. So Danish question is, how time is decided cause excess metal also solidifies? Tell me one thing, the thickness will depend on what? The thickness of the casting that you want to make will depend on what? The thickness of the casting that you want to make, it will depend on what? Any idea? It will depend upon the time. The thickness will depend upon the time. Thickness of casting will depend on time. Okay. So if you keep the molten metal for higher duration, you'll get higher thickness. Okay. So for thin casting, we can say tau is actually proportional to m square, right? Tau is actually proportional to m square for any kind of casting. For thin casting, the modulus is nearly equal to the thickness. For thin casting, the modulus not nearly equal to, it is equal to the thickness. Since here we are trying to make a thin casting, we can directly take the modulus is equal to the thickness. So we can say tau is directly proportional to thickness square, which implies T is directly proportional to root of the tau. Since this is an equation of degree 2, how many constants will be needed to remove this proportionality? How many constants will be needed to remove the proportionality? 2 constants will be needed, right? So T is equal to C1 plus C2 root over of tau. The thickness will depend upon how much time you are keeping the molten metal inside the mold. Okay, I'll repeat again. See, modulus is volume upon area. So let's say this is a thin casting. So what is the volume upon area? Volume is the area into the thickness. This divided upon the area. So what will be left? Only thickness will be left. Yeah, very good, Danish. That's what I was saying. What I am saying is, if you want to make a thin casting, there is a process called as slush casting. In this, what we do is, we'll take a mold of the required shape. On this mold, we'll pour the molten metal. On this mold, we'll pour the molten metal. The solidification will start from the mold wall, right? So the solidification has started from the mold wall. This shaded portion you can see. Once the required thickness has achieved, we will invert the setup. So when we invert the setup, all the excess molten metal will flow out. Then we will remove the casted component and we'll get the required casted component. Now, the next question is how to control the thickness. For that, I have written this expression. How we got this expression is the solidification time is directly proportional to modulus square, right? So for thin casting, you can see that the modulus will be equal to the thickness. So tau becomes directly proportional to t square. And we need to remove this proportionality. So whenever you want to remove the proportionality, you have to keep the number of constants equal to the degree. Since here the degree is 2, we will be using 2 constants. Therefore, t becomes equal to c1 plus c2 times of root tau. So thickness depends on for how much time you are keeping the molten metal inside the mold. Okay, so this is how we are controlling the thickness. Understood? See, this is the thin casting. What is the volume? What is the modulus? Modulus is volume upon area, right? Volume is this area into the thickness. Volume is area into thickness, right? So volume is area into thickness divided by area. Area will get cancelled. We'll be left with thickness. Okay? No problem. No need to say sorry. Okay? See, we have used a empty mold. In the empty mold, we poured the molten metal. Secondary screen you can see. Now the molten metal has started solidifying from the mold wall. Longer duration for which you are keeping, the thickness is increasing. You can see in the fourth diagram, the thickness is increasing with the time. Right? The thickness is increasing with the time. In the next diagram, you can see once the required thickness has been made, the setup will be inverted, and when we invert the setup, all the excess molten metal will flow out. And what we are left with only the casting. So this is how you have got a hollow casting. I don't know what they were trying to make, but they have made it. Okay. So this is slush casting. Slush casting is a casting process in which liquid molten metal is poured into a cavity and allowed to solidify. Invert the mold so that unsolidified metal falls downward. Okay. Break the mold to obtain the casting. Application is decorative parts like lampshades, Christmas tree parts, bowls, etc. Mostly it is not used for metals. It is generally used for plastics and all. If you go and check on the YouTube videos, it is mostly related with making of mask and all. Okay. Only hollow castings. Yeah. Hollow castings or thin castings. Okay. You won't be able to make solid casting. If you are making solid casting, it becomes the normal casting process, right? Overall, you can say thin castings, not hollow. You can say thin castings. Even though hollow castings are thin castings, right? So this is slush casting. Next is investment casting. So what happens in investment casting? In investment casting, first we make a pattern. How we make the pattern? We make the pattern by injection molding. In the first diagram, you can see we have made a pattern. We'll take out the pattern and we'll assemble these patterns on a assembly. We'll assemble these patterns on assembly. The assembly is looking like a tree. Okay. The pattern that we have used here is wax. In investment casting, we can use wax patterns also. We can use mercury pattern also. Okay. Once the wax pattern has been assembled, the entire assembly is dipped inside several coatings. Okay, this entire assembly is dipped inside several coatings. Once the coating is completed, once the desired thickness of coating is achieved, we'll keep the setup inverted and we'll heat it. So when we heat it, what will happen is all the solid wax, all the wax which was present in the form of pattern material, they will melt and they will flow out. All the wax that was present in the form of solid pattern will melt and it will flow out. Now what is left behind is only hollow cavity, only empty cavity is left. In this empty cavity, we'll pour the molten metal. We'll pour the molten metal, we'll allow it to solidify. After this, we'll break the mold, and we'll get the casting. Okay, everyone understood the process? Okay, so let's have a look at a video. Okay, so movie time. See, in this part of the video, they are showing how the wax patterns are made. The wax patterns were made by injection molding. Now several wax patterns have been made. Different wax patterns have been made. This is a real life example of how piston heads can be made. Now they are assembling. Yeah, Vishwas, that was a die. Okay, of injection molding. They are arranging the wax patterns in a tree-like assembly. Look here, Danish, focus on the video, you will understand. Simply a coating will be formed and that coating will slowly solidify. See, they are dipping the pattern. It is a ceramic slurry. So ceramic will automatically form a coating over it. See, they will dip it multiple times. No, slurry is not hot. Danish. It is normal temperature only. If it is hot, then the wax will melt, right? Just to increase the thickness, they sprinkled some sand also. They will dip it again to increase the thickness. Multiple dippings take place to increase the thickness. Okay. This process can be done manually also. So this is the manual one. Wait. So in this portion, they have cut the section, they have cut the assembly, and they are showing like how the pattern is filled or how the coating is formed. The orange portion that you can see here is the wax pattern. And over that the coating has been formed. Okay. And this is after the removal of the wax. That was after the removal of the wax. Okay. So see, here they have inverted the setup. They are putting it inside an oven. And they will heat it. They have inverted it so that after melting, all the liquid wax will flow out. Now they are pouring the molten metal. See, they have taken out the mold and they are going to pour the molten metal. Now by vibration they will remove the shell. By vibration they will remove the shell. See, these are the clean casted components. Now they will remove the individual components. Focus here. In this portion you will see that the surface that we are getting is so smooth. See, the surface we are getting is so smooth. So out of all the casting process, best surface finish we will get in investment casting. Best surface finish we will get in investment casting. Okay. Now they are taking the measurements. So this is the investment casting. I believe you understood. So let us see. Patterns are first made. Several patterns can be attached to a sprue to form a tree if required. The pattern tree is coated with a thin layer of refractory material and later covered with thick coating to make the rigid full mold. Heating of the mold in inverted position to melt the metal, to melt the wax and permit it to drip out of the cavity. The mold is preheated to a high temperature so that contaminants are eliminated from the mold. The molten metal is poured and it solidifies. The mold is removed from the finished casting. The pattern is made up of wax or mercury. Wax pattern is called as lost wax method. If we are using wax pattern, then the method is called as lost wax method. If we are using mercury pattern, then it is called as Mercast method. Slurry of very fine grained silica or other refractory in powder form mixed with plaster to bond the mold into the shape. So, in the upper portion we are talking how the pattern is made. The pattern is made up of wax or mercury. If the pattern is made of wax, it is called as lost wax method. If the pattern is made of mercury, it is called as Mercast method. Okay. In the next line, they are talking about the material of the mold. Slurry of very fine grained silica or other refractory in powder form mixed with plaster to bond the mold into shape. Advantages: complex and intricate parts can be cast. When I was teaching you wax as a pattern material, I told you one of the biggest advantage of using wax as a pattern material is that complicated shapes can be made. So hence in investment casting you can make complicated shapes. The tolerance of 0.05 mm are possible. If you remember the tolerance in case of shell molding, it was somewhere of the order plus or minus 0.25 mm. Here it is even lesser than that. Good surface finish is possible. In general, additional machining is not required. Near net shaped parts are produced. In the previous video itself, you could have seen the parts that were produced were nearly equal to the shape of the pattern that was required. So it is where it is used. Investment casting is generally used in precise machining processes such as jewelry, surgical instruments, blades of gas turbine, dental fixtures. Wherever you require very precise like measurements, precise readings, you will be going for investment castings. Okay. If jewelry you are not using investment casting, high tolerance will be there. You can't afford all that tolerance in gold and silver, right? Then surgical instruments, if they are not exact, if they are not accurate, surgery will not be performed properly. Blades of gas turbine, also they are made with complicated engineering. Dental fixtures, whatever fittings that are made inside the teeth. They take very accurate readings. They make very accurate components, right? How they are made? They are made by investment casting itself. So this is investment casting. Understood till here? This is very popular. The applications. Jewelry, surgical instruments, blades of gas turbine, dental fixtures. This has been asked in various exams many times. Understood till here?